Hello Math 1342 students. Let's begin lessons 13 and 14, inferences on two samples. Here at this level, we're going to consider two types of two-sample inference problems. Case 1, when we have two completely dependent data coming from two completely dependent samples, but both of those samples are coming from a single sample from a single population. For instance, a single sample just before and after. This is much easier case, and in this case it is possible to reduce the problem into a one sample inference, which we had been studying for several weeks. We're going to do that first. Now how about the other end of the extreme? What if we have two completely independent data coming from two completely independent samples which originated from either a single population or two different populations? Well, that's something we are going to consider in sections 2, 3, and 4. Now, what about somewhere in between? What if we have neither complete dependence nor complete independence? What if they are just correlated? Well, that's a bit different story, and we're not going to consider that here at this level. Okay, let's go over to two completely dependent samples just paired together. In that case, we simply take the differences. So one sample has x1, x2, x3, x4, and so on, and the other one has y1, y2, y3, y4, and so on, and we simply take the differences. And what we get, the mean of the differences turns out to be the same as the difference of the means. And then if we take the standard deviation of the differences, then we can do a one sample inference. Here's an example. 10 subjects with borderline high cholesterol levels were randomly selected for a study that involved taking a nutrition education class. Cholesterol readings were taken before the class and 3 months after the class. So we have before and after for the same person here. Same person, the third person, and so on. So these two data are completely dependent upon the selection of the person number 3. And these two are completely dependent upon subject number 5, for instance. Now in this case, we can simply take the difference between one and the other. And in this case, we took the difference pre-class minus post-class, and we can go the other way around. Pre-class and post-class minus pre-class, we can do that too. Either way it works out. Just the difference is a sign. And then we can do a one sample inference about the difference. So what we have a sample, or a single sample of size 10. Previously, we had two dependent samples of size 10, pre-class, post-class. Now, by taking the difference, I have one sample of size 10. And with this, we can find the 95% confidence interval. Yes, that's not too bad. I mean, we have size 10, so we can use the t-distribution of degree of freedom 9, kind of like this. And turns out this is the mean difference. Let's see. Yeah, these are the differences, and then if you take the mean of all that, it'll turn out 24.5, all right. And then plus the margin of error, t times SE, minus the margin of error, t times SE, where the t-score is associated to this 95% in the middle, or equivalently speaking, 2.5% to the right, associated to the degree of freedom 9. And if you set up and do the problem right, then you're going to get the confidence interval. How do we do that? Well, here it is. Here are all the sample statistics needed. You may need some calculator work, of course. That's the difference of the mean, or mean difference. And this is a standard deviation of the differences. You see, we have this samples of size 10, and then you can type those into MS Excel or something, and then find out the standard deviation. And here is the sample standard deviation for the differences. And then you get S over square root of n for your standard error. There you go. And then you use sample standard deviation over square root of n. So you have to use t distribution, not z distribution. And oh, this is just computation purpose. And then you can work it out like this. T score is end minus center over SC. You see? End minus center over SE. So this right-hand side endpoint minus 24.5 over the standard error we calculated. And that has to be the t-score associated to the 90% in the middle, 95% in the middle, excuse me, and the degree of freedom of 9. And the detail is left to the students. Never mind. I have t-table here. So let me just show you briefly. So you're looking for 2.5% to the end, or equivalently speaking, 95% in the middle. So you're looking at this column here. And then for the degree of freedom of 9, so 2.262, and plus or minus 2.262 because we have both right-hand side and left-hand side endpoints. So right-hand side and left-hand side. So t-score is 2.262, and calculating this to find out this x value, that's not too bad. Solve that equation and then work it out. You're going to get the left-hand side endpoint and the right-hand side endpoint, and that's how you get the 95% confidence interval. Something we had been doing all the time from lesson 10 and lesson 11a. So in short, even though we have two samples, we can reduce it into a one sample inference problem simply by taking the difference. Now, do we have enough time for hypothesis testing? Well, let's go ahead. Same data set here, and here's a question. Is there sufficient evidence to declare that this nutrition education class helps people reduce their cholesterol levels? Data set is basically this. And reducing cholesterol, so the null hypothesis is no difference. Null means no, so no difference, or the difference is 0. And then what do you think is the alternative hypothesis there? The difference is, well, there should be some positive difference, and that positive difference amount is the cholesterol level the people were able to lose, right? You can sort of like this. Difference is 0, or difference is greater than 0. Sometimes the problem explicitly says difference is greater than 460, kind of like that. But if it doesn't say, then you'll have to compare with 0. 99% of the time it's going to be comparison with 0, but in the exceptional case, if the problem explicitly gives you more than 75, less than 60, whatever it is, you just follow that. Here's the initial picture here. No difference versus, I want this critical value. And once you find out this critical value and compare that with the observed difference of 24.5, then I'm through. 24.5 falls here in the blue region, then close enough to the null, so null wins. If it falls in the red region, then too far away from the null, so we reject it and go with alternative. So how do you do that? N minus center over SE to find out this critical value, and t-score associated to this 1% is 2.821. Let's see, here's a t-table, and the degree of freedom is 9 and 1%, so 2.821. That's the number we use, and solve it. You get the critical value. 26 point something, so 24.5 falls into the blue region right here. So you go with the null hypothesis. Here we go. Now, if you repeat the problem with different alpha value, for example, you may get different results. For example, if I use alpha as just 5%, then you get different critical value and different conclusion. Let's go back to the original problem. Okay, that's one way to handle it, using the critical value approach. Now, what if I use the probability value approach? That's going to be a bit trickier because this is a T problem, and with the T table that are commonly available, you cannot find out the probability value directly. You'll have to use some other web-based statistical tool or something, or fancy calculator like Mathematica, like me. But in any case, you can set up like this, and then you're looking for this probability value. You see this time 24.5 directly here, and then looking for this probability. If this probability is big, then we go with the null. If this is small, then we go with the alternative hypothesis. And it turns out if you calculate the t-score, n minus n2 over SE, and calculate the probability, it turns out it's a bit bigger than 1%. So we go with the null hypothesis. And this probability turns out to be 0.0144 something. So if you compare with alpha value of 1%, then we go with null. But if you compare with the alpha value of, say, 2%, then you go to alternative. It all boils down to estimating this one, which can be a bit tricky. And in any case, here's a conclusion. Now, the probability value approach may not be that useful, but there's another way, confidence interval method or confidence bound method. Should have been called confidence bound method. You could find out the confidence interval around the observed difference of 24.5. And then where does the null 0 fall? Basically, you're doing this. You're looking for one-sided confidence interval or lower confidence bound and find out. And then null is 0, so null falls here in red region or null falls here in the blue region. Either way you can work out. And then you can do the same kind of computation, 99% lower confidence bound computation. And then we are going to the left, so negative t-score. Do some algebra, you're going to get the 99% lower confidence bound, or the one-sided confidence interval of negative 2.13 to infinity. And does 0 fall into this confidence interval? Yes, it does, because you see this is negative. So yes, 0 falls into the confidence interval, so it's close enough to this observed difference. So we go with the null hypothesis. It works this way too, but the overwhelming majority of the students prefer to use the critical value method, which we talked about as step 1. Alright, we went through 3 types of solutions. That'll conclude all the example problems here.